At this point, we've talked about the multiplication rule, unconditional and conditional probabilities. But when you're dealing with conditional probabilities, it's easy to get confused sometimes, especially when you're first learning it. So there are several tools that we can use to really understand what we're conditioning on and what quantities we're really trying to calculate. We've covered Venn diagrams. Those aren't great for understanding conditional probabilities. The joint and disjoint aspects of Venn diagrams are quite useful. So I would say Venn diagrams are really more useful if you want to understand the addition rule, but they're not so great for the multiplication rule and conditional probabilities. However, there's something called probability tree diagrams. Often students find them quite useful for understanding the multiplication rule and working with conditional probabilities. As well, many students find probability tables quite useful. These are not the only ways of working with probabilities, but these are often useful for many students. And in fact, I should also mention that you don't have to use any of these tools. You don't have to use probability tables or probability tree diagrams or even Venn diagrams. But when people are first learning probability rules, it's often useful to go through some of these. So let's look at probability tree diagrams. We've covered Venn diagrams, which are useful for the addition rule. Now let's look at probability trees for conditional probability. Now what is a probability tree? The idea is that you can visualize chains of probabilities by looking at different conditioning events. So here's a very basic probability tree. This tells us the probability of flipping one coin, a fair coin. So you can see that we have two branches, okay? And each branch has its own probability. So the probability of getting a heads is 0.5, and the probability of getting a tails is 0.5. And you can see at the end of each branch is some outcome in the sample space. So we have two outcomes in the sample space, heads or tails. So that's why we have two branches. But you might want to say, okay, this is just one coin flip. But what's the probability of flipping heads twice in a row? Well, what you do is you just add more branches. So this tells us the probability of flipping heads twice in a row. So to calculate the probability of flipping heads twice in a row, you just multiply down each branch. So you can see if you flip a coin once, the probability of getting heads and tails is 0.5 each, respectively. But then you can see, if you want to see what's the probability of getting heads and then heads again, you multiply 0.5 times 0.5, and you get a probability of 1/4, or 0.25. So you can see that one way of working with conditional probabilities is to understand that in a probability tree, what you're doing is you're multiplying across and you're adding down. So for example, in this case, to find the probability of flipping a heads and then a heads again, you multiply 0.5 times 0.5. And then that will give us the joint probability, the probability of getting a heads and a heads. If you want to find the probability of getting heads and tails, you multiply, you just follow the branch up to the first event of getting a heads and then the second event of getting a tails. And you could just calculate the probability by multiplying those two branches together. And then finally, if you want to find the probability of tails and heads, as well as the probability of tails and tails, you can find that those are also each have a probability of 0.25. And then when you add down each of the set of branches, you can see that the total equals 1, which is exactly what you expect. The sum of those joint probabilities, it's just going to equal the probability of the overall sample space. Just to kind of emphasize the structure of a probability tree, okay, we have, in the generic sense, besides flipping coins, we have, if you just have one sort of event, B, you can express it in terms of the probability of B and the probability of not B, the complement. And then you have two outcomes, B and not B. And then we add those two probabilities together, the probability of event interest, B, and then the probability of not B, that sample space, the probability is going to equal 1. But it's also useful to look at the sort of structure when we're looking at conditional probabilities, because if you recall, flipping a coin, a fair coin, we treat each event as independent. So we use, in that first example, we really weren't looking at conditional probabilities. But when we work with conditional probabilities, the notation is slightly different because each branch, okay, each initial branch is in fact an unconditional probability. But then for the second set of branches, you can see that they are in fact conditional probabilities. The rules are the same. You multiply across and add down. So just to be clear, those first two branches, okay, we have B and not B. So the overall probability of getting event B is labeled, and we have the overall probability of not getting B. The second set of branches tell us the probability of either getting A or not A, but conditional on B or not B. So that first branch, for example, tells us, we can see that the probability of A given B is labeled for that second branch. So let's go over this a little bit more clearly. So this branch right here, labeled in blue and green, the blue branch tells us the overall probability of B. That green branch, it tells us the probability of A given B, because B just occurred. And then if you multiply those two branches together, those two probabilities together, you get this joint probability of A and B. That's the multiplication rule. Okay? That next set of branches tells us the probability of B and not A. So you can see that that first branch, we still have the overall probability of B, and then the next branch, that green branch, that is the branch telling us what's the probability of not A, conditional or given on B. And again, to find that joint probability, you just multiply those two branches together. That third set of branches, again, in this case, we have a slightly different overall probability. We're conditioning on not B. So we have a probability of not B, and then that second green branch, that tells us the probability of A given not B. And then to find the joint probability of A and not B, you just multiply those two probabilities together. This final set, we're trying to find the probability of not A and not B. So that first branch, labeled in blue, that's the overall probability of not B. And then that green branch, that tells us the probability of not A given not B. And we can multiply those together. Now in this setup, again, what we're doing is we're multiplying across to find the joint probabilities at the end of each set of branches. And so since we have B and not B and A and not A, we're going to have 4 different joint probabilities given at the end of these branches. And just to be perfectly clear, these probabilities add down so that the sample space equals 1, because these 4 joint probabilities, they're going to equal 1. Also recall that if you just look at the probability of B and not B, that sample space, that's going to equal 1 as well. The probability of A and not A, each of those branches, those are also going to equal 1. All right, so here's sort of an example with health insurance, looking at a probability table as well as a probability tree. So we might ask, given or if a person is poor, what is the probability of having no health insurance? So let's label each of our events. We have 2 variables, health insurance and poor, but we can think of really 4 different events, or to put it another way, we have 2 events and their complements. We have poor and not poor, so we have P and the complement of P. Then we have I for being insured and the complement for being not insured. And we can label these in our probability table that we calculated earlier, which is based on a real data set and is really just a table of unconditional proportions. So we might ask, given a respondent is poor, so given P, what is the probability of having health insurance? What's the probability of I given P? Well, we can use the multiplication rule in combination with our probability table. So the probability of I given P equals the probability of I and P divided by the probability of P. So the probability of P is simply the probabilities of these 2 cells. Okay, so it's 0.09 plus 0.29, which is 0.38. So you can also just look at the margins. Overall, roughly 38% of the population is poor. Then that joint probability is given by that cell in which we have I and P. So that joint probability is 0.29. To put it another way, 29% of the people in this data set are poor and have health insurance. And so to find the probability of I given P, we divide 0.29 divided by 0.38, and we get 0.76. So we can say, given the respondent is poor, what's the probability of having health insurance? It's still pretty high. Okay, about 3 out of 4 people who are poor will in fact have health insurance, or the probability is 0.76. You're more likely than not to have health insurance given a person is poor. We can also visualize this and understand this using a probability tree. It's exactly the same as using a probability table. So again, we're trying to find the probability of having health insurance given a person is poor, the probability of I given P. So when we write a probability tree, the first thing we want to do is we want to say, what are we conditioning on? Because when you write a probability tree, that first event that you write out, those first 2 branches, that's going to be whatever you're conditioning on. So in this case, since we're conditioning on P, that first event will entail P and not P. Okay? And then after that, the other 4 branches are going to tell us the probabilities of I given P, the probability of not I given P, the probability of I given not P, and the probability of not I given not P. So you can see that the overall probability of P, okay, is given by 0.38, and then not P is 0.62. And when we multiply each of those branches across, we get these 4 joint probabilities. Those are the joint probabilities given in the cell. So if you look at those ends of those branches, okay, so we have 0.29, 0.09, 0.59, 0.03. That all equals 1 because those probabilities sum up to 1. And those are equal to the joint probabilities from the probability table that we just saw earlier. But you can see that working with a probability tree is quite easy because we want to find this joint probability using this table. So what we can do is we can just multiply across. Now we might also want to say, given the respondent has health insurance, what is the probability of being poor? This is a slightly different quantity. We're trying to find the probability of P given I. So we can use the formula for the multiplication rule, the probability of P and I divided by the probability of I. So the probability of I is the sum of 0.59 and 0.29. That's 0.88. That's just the marginal or unconditional probability of having health insurance. Overall, 88% of the population has health insurance. But the joint probability is, again, 0.29. So the probability of P given I is 0.29 divided by 0.88, and we get 0.33. So given a respondent has health insurance, what is the probability of being poor? About 1 out of 3. Okay, it's, you're less likely than not to be poor given that you have health insurance. Right? This emphasizes why conditioning matters, because these 2 quantities, the probability of I given P and the probability of P given I, they are not the same. So here's the probability of I given P, and here's the probability of P given I. You can see that the joint probabilities are in fact the same, but the denominators are different. The probability we're conditioning on is in fact different, and that affects the conditional probability that we calculate. So for example, the probability of I given P, we're conditioning on that probability of being poor, which is only 38% of the population, which is high, but it's not as large as the probability of I, which is 0.88, which is really 88% of the people in our data set. So the joint probability is the same, but what we're conditioning on affects that denominator. And the larger that denominator, then you can see that that conditional probability gets smaller. So in this case, the probability of I given P, the probability of having health insurance given you're poor, is 0.76, and the probability of being poor given you have health insurance is in fact 0.33. Now you might ask, is having health insurance independent of being in poverty or being poor? How do we know? Well, we can use what we know about independent events multiplying together to find some joint probability to actually test a probability table to say, are these events independent? Are these 2 variables, in fact, independent? So we can show that having health insurance is not independent of being poor. To put it another way, there's some relationship between these two variables by looking at the probability of P and I. Does it equal the probability of P times the probability of I? So the probability of P and I should equal the probability of P times the probability of I if they're independent, but they don't. Okay, so we know that in this case, 0.09 plus 0.29 times 0.59 plus 0.29, those quantities, they do not equal the actual joint probability of 0.29. So we can say these two variables, in fact, are not independent. This is sometimes called the corner rule, and it's a very useful rule for figuring out whether two variables are related in a probability table. Now with that, we're ready to move on to this concept of relative risk as a measure of association. You can compare these joint probabilities with the overall probabilities to find whether two variables in a table are related, but more formally, we can use conditional probabilities to find out measures of relative risk. It's a basic measure of association. What it is it's a ratio of the probability of an event occurring in some exposed group to the probability of that same event occurring in a non-exposed group. Again, this is widely used in various fields like public health, psychology, sociology. In some fields, the concept of exposure is straightforward. So you might say secondhand smoke exposure. You might say another form of exposure might be having someone in your social network who has a disease. That increases your likelihood of actually catching that disease. So exposure can be straightforward. More generally, though, you can see exposure referred to as different conditions or life events. So for example, you might say poverty is a kind of exposure. It's in a way a risk factor for other outcomes. So by exposure, we're using it in a very general sense. The relative risk, or sometimes called the risk ratio, it's simply a ratio of conditional probabilities. Relative risk is the probability of an event occurring given you've been exposed to some event, B, divided by the probability of event given you're not exposed to that particular event B. So one very good aspect or useful aspect about the relative risk or risk ratio is it tells us the direction and magnitude of an association when we have two binary categorical variables, an outcome, some event, and some exposure. Right? So typically when we look at the sort of event, we frame it in terms of some adverse event. You don't have to do that, but that's why they call it a risk, okay? Because you might say, what's the probability of getting a disease? That's the event of interest, given someone in your social network also has that disease. So to interpret relative risk as a measure of association, you can say that a relative risk of 1, it means that there's no difference in risk between the two groups. To put it another way, there's no association. A relative risk less than 1, it means the event is less likely to occur in the exposed group than the unexposed group, while a relative risk greater than 1 means the event is more likely to occur in the exposed group than in the unexposed group. Substantively, you can think of interpreting relative risk or the risk ratio in terms of times the risk. Okay, so a relative risk of 4, it's greater than 1, and you can say that that would indicate the exposed group has 4 times the risk of having the event occurring. So that's how you express a quantity for relative risk. You say 4 times the risk. Or if it were 5, you'd say 5 times the risk of having the event occurring. A relative risk below 1, you would say, for example, 0.5, you would say that the exposed group has 0.5 times the risk of having the event occurring. You can actually see that the event is less likely to occur, is suggesting there's some kind of protective factor with the exposure. So let's look at the example of being uninsured. We're going to calculate the relative risk of having no health insurance based on whether or not you live in poverty. So the exposure is being poor versus not being poor. So in this case, we're going to look at not being poor as the exposure event. And then we can also look at some outcome or event. In this case, we're going to look at not having health insurance versus having health insurance. So for the relative risk, we want to say the probability of event given exposure divided the probability of the event given no exposure. So the event here is the probability of not having health insurance, and the exposure is the probability of being poor or growing up in poverty. So in this case, we're going to calculate the probability of having no health insurance given you're poor divided by the probability of having no health insurance given you're not poor. So when we do those calculations, you can see that the probability of having no health insurance given you're poor is 0.09 divided by 0.38, which equals 0.24. The probability of having no health insurance given you're not poor is 0.03 divided by 0.62, or 0.05. That ratio of conditional probabilities, that risk ratio, is 0.24 divided by 0.05, or equivalently 4.8. All we're doing is we're calculating the probability of not having health insurance for two groups. The exposure group here consists of those people living in poverty, and the people who are not exposed are those who are not living in poverty. And then we compare these two conditional probabilities. Again, if poverty had no sort of association with having health insurance, then you'd expect a relative risk of 1, meaning the probability of having no health insurance given you're poor would equal the same as the probability of having no health insurance given you're not poor. But the fact that these two quantities differ tells us something about these two variables. And in fact, we have this risk ratio of 4.8. Since this is greater than 1, we know that this exposure of living in poverty suggests an association, it suggests an increased probability of in fact having no health insurance. So what we can say substantively is that people who are poor, based on this data set, have 4.8 times the risk of being uninsured than those who are not poor. To put it another way, you can say that growing up in poverty is in fact some kind of risk factor for not having health insurance. You can also just emphasize what we're doing here is we're calculating two quantities, right, based on different sets of values. So this is for the probability of the event given exposure, and we use these quantities for the probability of the event giving no exposure, right? There are a few problems or limits, at least, to this concept of relative risk. Okay, first of all, this association, it's not a causal relationship. It's tempting to say, we might say, poverty causes having no health insurance. But all we're really saying is that there's some kind of association, right? This is an observational study. There could be some other causal factor, some lurking variable going on that's really explaining what's going on. However, we can say that poverty is some kind of risk factor. There's some kind of association for not having health insurance. Another caveat about relative risk is that it is called relative risk because it doesn't tell us the actual or absolute level of risk. So you might have some event with a very high relative risk, but it might not actually be that risky overall because the events are rare. So for example, some studies have shown that CT scans, if you have a CT scan as a child, you're 3 times more likely to have bone cancer as a child. The issue, though, is that these cancers are so rare that the increased actual risk is about 1 in 10,000 people. Bone cancer is very rare among children, so that relative risk might be quite high, but the absolute risk is very, very low. A few things to know about conditional probabilities and relative risk. Conditional probabilities, all we're really doing is you can think of it as subsetting some part of the data. We're just saying, given B, what's the probability of A, given some subset of the data. We like independent events because they multiply together to find joint probabilities. If A and B are independent, you know that the probability of A times the probability of B equals the probability of A and B. And we can use that with 2x2 tables to understand if two variables are in fact independent or dependent. But often, independent events, they really don't exist in most instances. We like independent events because they make calculations easier, but in reality, conditioning really often does matter. We can use what we know about conditional probabilities to calculate relative risk, which is simply the ratio of the probability of some event occurring in an exposed group to the probability of the event occurring in a non-exposed group. Relative risk is simply this ratio. A relative risk of 1 means there's no sort of association, but relative risk greater than 1 or less than 1 shows us something about the associations. We typically interpret relative risk in terms of times the risk. So for example, if you have a relative risk of 3, you would say you have 3 times the risk based on some exposure. And with that, we are going to conclude our discussion of conditional probabilities and relative risk.